Hey everyone, we're going to get started. So today we're going to cover the first of our three-part series of GPT and PyTorch. We're going to be covering how language is represented in a machine learning model. So as always, let's go into Google Drive and create a Colab notebook. So hit New, More, and Google Colaboratory. I'm going to start with pre-text block. Okay, so GPT and PyTorch. And today we're going to be talking about word embeddings. Actually, character embeddings more accurately, but embeddings and language representation. Okay, so the key thing I want you to take away today is how language is represented in neural networks. So far we've been working with numerical data. For example, in lesson 1, we talked about how to make a quadratic predictor, right? So you take some number as input x, and the model would predict the value of x squared. So this is numerical data because we take in a numerical input x and output numerical value x squared. And in CNNs and PyTorch, we went through how to classify images. And this is again numerical data because images are comprised of pixels, and pixels have intensities. So you might have like a 200 by 200 by 3 image, and every value in that image ranges between 0 to 1. And then through the model, it'll be it'll generate an output that's either 0, 1, 2, etc. all the way through your last class 9. So this was our quadratic, and we also have our image convolutional neural network. So these are the types of data we've worked with currently so far, pure numerical and also image data, which is also numerical. And today we're going to talk about how we represent words and language in a neural network. So can anyone take a guess at how we would represent a word in a neural network? Yeah.
As a vector with like different dimensions.
Yeah.
Depending on what task you're trying to solve.
Yeah, that's right.
Yeah.
Why do we want to represent a word as a vector?
It's easier to process numerically.
Yeah. What about semantically?
I mean, it depends. If you have like maybe a task that, I don't know, you have to figure out how intense a word is and how positive a word is, you can represent it in 2 dimensions. So it sort of helps semantically. I don't know what it's.
Yeah, okay. Good point. So what we're talking about right now is representing words is what's called an embedding. So an embedding is a vector representation of a word. You recall from math that a vector is essentially a sequence of numbers. So a vector is a sequence of numbers, for example, like 0.3, negative 1.2, 5, 7, etc. Right? So we have a certain number of elements in each vector, and each vector is a list of numbers. And an embedding is the idea that we use vectors to represent words. So like words, when you and I converse, we don't think of vectors, but we'll convert them into vectors for the purpose of feeding it into the neural network. And there's a couple of interpretations of vectors that help us in this. So the first is a list of numbers. And the second is a magnitude and direction. So the list of numbers perspective is useful to us because it's really simple to represent in machine memory. It's just a contiguous list of floating point numbers. And the second, magnitude and direction, gives us a semantic interpretation of embeddings. So the idea of this is, like, let's say we have the embedding of the word good as like 0.3, 0.2, negative 0.5, 0.7. Perhaps the word great is just a scalar multiple of this. Like great might be like 1.2 times good. Does that make sense? And we can multiply each of the elements within good by 1.2 to get an estimate for what the vector great might be. And so vectors carry some amount of semantic information in words. So a vector represents essentially a point in space. You can imagine it as a point, and like the arrow emanating from the origin to that point is the vector, right? And if we consider these 4 words, we can more closely study the semantic relationship between vectors. So the 4 words are man, woman, king, and queen. And if we think about how these are represented, if we know all of these 3 words, king, man, and woman, how can we represent the word queen in terms of mathematical operations between these vectors? Do you remember vector addition and subtraction? So it would be like king, the vector king, like emanating from the origin to this blue point, minus this vector man, plus this vector woman, is approximately equal to this vector queen. Does that make sense? So like these are coordinate points in 2 dimensions. And if we take these coordinate points, like let's say it's like 1, 2, and this is like 0.5, like 1.5, you can subtract man from king, and then add the vector for woman, and you'll arrive at the vector for queen. So vectors allow us to represent semantically what words are. This is also really nice because we can feed these numbers directly into the first layer of a neural network. And so this is essentially the approach we're going to use to represent text in neural networks. There's also a couple of other things that we need to take care of when representing text in neural networks. In general, we're going to have sentences, like, for example, the dog jumped over the fence. This is a sentence, but we want to process like 1 word or 1 character at a time. And so when you break this sentence up into smaller units, that's called tokenization. I'll say dividing. And the smaller units are typically words or characters. Today we're going to do character level tokenization, which is the simplest. If you just have like a string, like for example, I'll say sentence. The dog jumped over the fence. We can convert it into a list of letters just by passing it into the list function. Right. And now we have the list of tokens. Each unit, either a character or a word, depending on what level you're dividing it into, is called a token. And in this case, since we're using character level tokenization, each character is a token. So we have the first token is T, the second token is H, the third token is E, and so on. So character level tokenization is great because it is very simple, although it's not used as much in practice because it doesn't have like a lot of semantic, there's not much semantic meaning in each letter as opposed to each word. But we're going to do this today because use character level tokenization today because it's the simplest. The second thing that we need to think about is once we have these tokens, how do we convert it into a vector, right? And the way we're going to do this is we're going to form what's called an embedding matrix. So to create an embedding matrix, you can import PyTorch, and then you can define embeddings matrix, also import the neural networks part of PyTorch, and then .embedding. This 3 represents the number of embeddings. This 10 represents how many elements are in each embedding vector. So this is going to be a 3 by 10 matrix representing 3 embeddings. And if I want, I can print out what the result of embeddings is. and this doesn't tell me a whole lot. It's just a 3x10 embeddings matrix. But the way we use embeddings is we call which embedding we want. So if I want to get the first embedding, I would index it with 0, or I think I would actually pass in 0 because this is a neural network layer. And I have to give it a tensor, not an integer. So this is a 10-element vector that is the first embedding in the embeddings matrix. And these are just random values because we haven't trained any neural network. To get the second embedding, I'll just pass in 1. And to get the third embedding, I'll just pass in 2. So these are the embeddings that we have. Now we need to go from these text characters into these embeddings. What is the simplest way you can think of to do that? So I need to get like this number here from these characters. I need to map a character to each number. We can probably just start from the top and assign a number to each one, right? So like T is the number 0, H is the number 1, E is the number 2, and so on, right? And then once we find a character that we've already seen before, like for example, this O and this O, then we can assign it the same number as the O we assigned before. Yes?
You just use a set.
Yeah, can you elaborate?
You use like a set as like a dictionary as like a key value. Like you can assign a number, like each character number in a set.
So a hash map, right?
Hash map,
Yeah, yeah. We can, yeah, exactly. We'll do that. We'll use a hash map. Yes?
What about like getting the ASCII code directly?
Yeah, that can work too for character level tokenization. There's a couple of issues with that though. One issue is that you're not necessarily going to use every ASCII character. So if you like instantiate this embeddings matrix to have every single like ASCII character, there will be like a lot of rows that like you'll never use. And the second issue is that we're using character level tokenization, but in most neural networks in production, you won't use character level tokenization. We're using this for simplicity, but in practice, you'll use word level or subword level tokenization instead. Yeah, but good idea. So let's go with the hash map approach because it's simple and we can also extend it to words if needed. So the idea is we're going to go through this list and we're going to convert each word to a row. So for example, if we were doing like word level tokenization, we would convert cat to 0, for example, dog to 1, mouse 2, and so on. We're not, so let's build our hash map of characters. And the way we're going to do that is we're going to define a function of build tokenizer. This is going to give us a vocabulary which maps each letter to a number. So it's going to take in some text. I'll define like our data set up here. Text equals, and let's use the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. There's our data set. And we're going to instantiate both a vocabulary, which is that hash map we talked about, and a reverse vocabulary that goes from the number to the character. Can anyone tell me why we want a reverse vocabulary? So the reason we want a reverse vocabulary is because the vocabulary is what we're going to use to feed into the model, right? So we have text, we'll convert it into numbers, and these numbers are going to be rows that we're going to feed into the embedding layer. But when we get an output from the model, it's also going to be in the form of a number. But like when you talk to ChatGPT, you don't want like a list of numbers. That would kind of suck. And so we need to convert it back into text. And so that's what the reverse vocabulary is for. So what we just described is that we're going to iterate through every character in the text. And for every character, if it's not in the vocabulary, then we're going to add it to both the vocabulary and the reverse vocabulary. So what this is doing is we're setting the vocabulary hash map at the current character to the number of elements currently in the vocab. So if there are no elements in the vocab, this is going to be 0. If there's a single element in the vocab, it'll be 1, and so on. And every time we do this, the size of the vocabulary will increase by 1, and therefore we'll get a new index for that character. We likewise do the same thing for the reverse vocabulary, except we have to put this before this line, right? Because if we put it after, then the size of our vocabulary has already increased and will be off by 1. You can play around with this to see exactly what I mean. And at the end, we're going to return both the vocabulary and the reverse vocabulary. So let's get a vocabulary and reverse vocabulary from the text. And let's check like what is the vocab at O. Let's actually do like D for simplicity. So run this, and we'll see the value is 3 because D is the third letter in the text, or fourth letter. Here's what vocab is. It maps each letter to a number. In this case, since it's the alphabet, we'll get like the numerical equivalent. So A is 0, B is 1, C is 2, and so on. But for a different data set, the order might not be the same. And the reverse vocabulary will be the same thing, but backwards. Now let's define a data set. So recall that in PyTorch we can define a data set by extending the dataset class. So I'll import both the dataset and data loader, and I'll create a next token dataset. And recall that to instantiate a dataset, I need to implement 3 methods. The first is the initializer. The second is the length of the dataset, so how many items are in the dataset. And the last is what is at each index of the dataset. This should have an S, torch.utils.data. So what this dataset is going to give us is it's going to give us the next token for each current token. So what I mean by that is we want to use this alphabet to train a model that will predict the next character of the alphabet. So if I give the model A, it should give me B. If I give the model W, it should give me X. And the way I'm going to do this is I'm going to take in the set of all tokens. I'm going to store all the tokens within the class, but I'm going to store it in the form of a tensor. In get item, I'm going to return the tokens at the current index, the index being requested, as well as the token at the next index. And when I return the length, what should I return here? So the first value is will essentially be like 0, comma 1, representing A, comma B. And the second value in the dataset will be 1, comma 2, representing B, comma C, and so on. How many elements are there in this full data set? So the last element will be Y, comma Z. And this should probably be 24, 25. So how many elements are there in this data set? Yes, why 25?
I don't know, I just basically counted the second part of the tuple.
Yeah, I mean, that's correct. But like more specifically, the reason is that we have a total of like 26 elements in the tokens. And each time we're iterating over like an element of the data set, we're using like 2 of the tokens, 2 consecutive tokens. So like in the first one, we'll take A and B. And so the last element will have, the second element of that tuple will be B. And so if we keep iterating through the end, we'll get to Z. And you can't go farther than Z. So B through Z is 1 through 25, which is, as you said, 25 in total. So for that reason, we can't return the length of self.tokens. We have to return the length of self.tokens minus 1. There's 26 letters in the alphabet, but there's 25 pairs in our data. OK. So that's how you define the data set. Let's inspect the data. So actually, I'm going to write some helper functions for us. First, let's define an encode function. This will take a given text and encode it into these token indexes. Because otherwise, like, we have these this text, and we have this tokenizer, the vocab and reverse vocab, but we haven't put them together. So let's put them together now. We're going to write an encode function. It takes the text and the vocabulary, and we're just going to return the, for every character in the text, we're going to return the vocab of that character. We'll also define a decode function that will take tokens and a reverse vocabulary. And here what we'll have is we'll have the text that is represented by a set of tokens. So for every token of these tokens, we're going to index into the reverse vocabulary. And since token is a tensor, we're going to call .item to get a scalar and look up that hash map. Run this. So let's take a look, for example, at what is decode of dataset 0, reverse vocab. I didn't actually define the data set, so let me instantiate it. I didn't build, OK. So to get these tokens, I'll need to encode. And let's run this block, and we'll get AB, right? So to be clear, what's happening is that we're taking the first row of the data set, first item of the data set, which is 0 and 1, and we're passing it to our encode function, which will run through all the elements of this tuple, and it'll convert it to the equivalent, or we're passing it to decode, which will run through all the elements of this tuple and convert it to the corresponding character and concatenate it. So that's what we're getting here. So 0, 1 is equivalent to AB. And we can do the same thing for like starting at 3, and we'll get DE corresponding to, should be 2, 3. Let's now define our data loader also, which will be very simple. We'll just set a batch size. In this case, since our data set is so small, I'll just set the batch size to 1. I'll pass in the data set to the data loader, and set the batch size to the batch size we defined. And now we have our data ready for us. Now we need to define a model. So we've handled the data, and now we need a model. So the data, just to be clear, started in the form of like the dog jumped over the fence, and it got converted into a set of numbers like 0, 1, 2, 3. These spaces will also be tokenized, by the way. 0, 1, 2, 3, and then like 4, 5, 6. And this will go back to like 3, for example, if we were tokenizing this sentence, because we've already seen this space before, and so has a value in the hash map. And we'll just keep going. So it gets converted into this representation. And then we're building a data set of tuples like 0, 1, 1, 2, and so on. And like here, like 6, 3, right? So every character and the subsequent character. And then this is our data set. And we're also passing this to a data loader. And this is like what we've done to get our data in the format that we want it to be. And so this is like our raw data. We've tokenized it. So this is the encode step. This is this sentence. This is the encode step. This is where we convert it into a data set. This is data set step. And then this is the data loader step. The formatting's a little off, but I hope that makes sense. So now that we have our data in exactly the format we want, let's define a model. So recall that to define a model, we need to extend nn.module. And so the model that we're going to be creating today is called a bigram model. We need to give it an initializer and a forward function. In the initializer, we always need to register the model with PyTorch, like so. Otherwise, we'll get an error in calling the forward method. And in the forward method, or one more thing, we need to define embeddings. So we'll take the vocabulary size, and that'll be the number of rows in our embeddings table, and also the number of columns in our embeddings table. And what we'll return is self.embeddings of the row that we're passing in. So what have we done here? What we've done is, given a vocabulary size, we construct an embedding table of that vocab size by vocab size. In the forward function, we just do an embedding lookup, so we'll just retrieve the vector at that row. So if we get 2 in the forward function, we'll get the second or third embedding. This is called a bigram model because what this is modeling is just the probability of a character following another character. So here we're like getting there's like a certain probability that 3 follows 6, for example, and a probability that 2 follows 1. And we're going to train it to represent those probabilities. And so in fact, these embeddings are not going to be a semantic representation of characters, but rather the probability that a certain character follows another. So what I mean by that is the first embedding is going to represent like let's say this is the embedding vector for the character A. It's going to have the probability that A follows A. So this is a probability that A follows A, which is actually going to be 0 in our data set because A never follows A. Then the probability that B follows A, which is 1 because whenever we have an A, B always follows. And then 0 and 0 and 0 and so on. This is what we want it to learn. And B will be the same thing, but it's always going to be followed by C. And so on. Does that make sense? So what a bigram model does is it actually stores the probability of each value here. So this is the probability that A follows A. This is like the probability that B follows A. This is the probability that C follows A, and so on. And so these embedding vectors actually represent probabilities. So let's instantiate this bigram model. The vocabulary size is the length of the vocabulary, which should be 26. And we'll instantiate a bigram model of the vocabulary size. So I'll run this, and I'll run this. And now we have a model. Let's look at like what the outputs are for like a given row. Let's say like the 4th row, which will represent as 3. and they'll just be 26 random numbers. So this is the probability that A follows D. It's probability that B follows D, probability that C follows D, and so on. And these probabilities actually will not be probabilities between 0 and 1. And the reason is we didn't enforce any kind of probability constraint here. Embeddings can like range from anything to anything essentially across all real numbers. What's going to happen is that when we define our loss function, the loss function will implicitly encode probabilities for us. We'll see what that means really soon. Let's write the training loop. So we're going to set some of our hyperparameters. I'll set the learning rate. I'll set the optimizer. I'll set loss function, so number of epochs, let's say 100, and I'll store the losses of each epoch so that we can graph them. And for every epoch and epochs, we're going to start the epoch loss for that epoch as 0, and we'll average it across the batches. And so for every X batch and Y batch in the data loader, we'll set ypred equals model xb. So we'll get the prediction for that batch, and then we'll calculate the loss as the loss function evaluated on the predictions and the true y's. We'll call loss.backwards to get the gradients. We'll step the optimizer to apply those gradients to the model parameters, and we'll zero the gradients as always. Then we'll add the current loss that we calculated to the epoch loss, and every epoch will print the epoch and the epoch loss. Finally, we'll append the epoch losses to the epoch loss. So let's run this. Oh, that's interesting. So this should be epoch loss dot item. That's why we're getting such strange output. So let's restart it. I'll redefine the model up here. So I'll rerun this. I'll run this again. There we go. So we can see that every epoch, our loss is decreasing until we get to a loss about 2.5. And let's see what our model, let's see the loss function graphed. So we'll import matplotlib and plot the epoch losses. It should be matplotlib. And you see that like they decrease quite a lot per epoch. Now let's generate. So we can technically generate from the model like right now. So we could like take the model and pass it in like torch.tensor 0. This will represent A per our hash map previously. If we pass this in, we'll get a set of numbers, and you can see like the maximum value is going to be 1, or like corresponding to this index 1. So what this is called the argmax. So I think I can write like torch.argmax. And so I'll get the value 1. So this means that B is most likely to follow A because we train it on the alphabet. And if I plug in 2, then C is most likely to follow B, and so on. The issue is that this is not a very nice way to interact with models. So let's write like a helper function to display the outputs more nicely. So I'll define a function called generate, and I'll take an initial start character and a maximum length. So I'm going to first encode the character that's given using our encode function in the vocabulary. Then I'll start a tokens list as token. So this is actually going to be a list based on the way our encode function is set up. And then I'm going to iterate and for each iteration, I'm going to get the value that the model returns. So this is going to be the token, and we're going to wrap it in a tensor and make sure that the type of the tensor is a long rather than a float. Otherwise, the indexing will throw an error in the embedding layer, because the embedding layer expects a long or integer as the input. And we're going to append that to the current tokens. And we're going to return the decoded result of all this. So we've defined our generate function. And let's start with L and generate the next 10 elements. You can see we get L, M, N, O, P, Q, R, S, T, U. So we've trained a bigram model that predicts the next letter of the alphabet until a given number of characters. So if we start with A, we'll get the first 10 elements. If we start with like C, we'll get like C, D, E, F, and so on. So that's how you represent a text in a neural network and train like the most basic neural network possible to work on text, the bigram model. Now, you might be thinking like, what's the point of this? You probably could have written much shorter code to do the exact same thing. But the difference is that we've now taken a different approach to representing language. So instead of like working with text as strings, we're now working with text as embeddings, as vectors, as rows of an embedding table. And what we'll see later is that the embeddings that we looked at, this nn.embedding, nn.embedding, this embedding layer, let me find the model definition. Yeah, this embedding layer will also be the first layer to GPT. Yes, question?
In this embedding layer, we have like 26 elements, so like it's a 1 by 26 vector, right?
Yes.
So if we have like something like words, and if we have like a lot of words,
yes.
Is it that the embedding vector is proportional to unique words?
Yes, exactly. The number, each row of an embedding vector is the embedding for its corresponding word. And so the number of rows in the embedding vector, in the embedding table, is exactly the number of tokens. So
what are the columns?
So the columns, what's interesting is that because we're defining a bigram model today, we're defining a probability that each token follows each other token. And so we have to have like the probability, so each row needs like the probability that A follows it, and the probability that B follows it, and so on all the way to the probability that Z follows it. And that's why we have like the number of columns equal to the number of rows. In general, you won't be using embedding bigram models, so you can actually set this to whatever you want. This could be a 100-dimensional vector, it could be a 1,000-dimensional vector. People oftentimes like to express them in powers of 2. And we'll call this like the embedding dimension. So you can like set a variable called embedding dimension and set it to 128 and pass that into here. It can be whatever you want.
But if we had like a bigram word model, so like, obviously in like a big data set you have like, I don't know, maybe 1,000 or 2,000 unique words. Will it be like
yes.
Each embedding will be 1 by 2,000 vector?
Yes, if you have a bigram model, then you need the probability that each word follows it. If there's 2,000 words, then each embedding vector will be the probability that like each of the 2,000 words follows it. Yeah, so the bigram model does not scale very well. If you have like 10,000 words, you now need a 10,000 by 10,000 matrix. Yeah, any other questions? Yeah.
So if you try to predict the next like 10 words after C, does it just pick whatever has the highest probability since it's not mapping to anything? Like, that makes sense.
So
Like what follows Z, like A,
what?
B, C,
Yeah, what's
D.
happening here is that if we look closely at this generate function, we're appending this token here, and in each iteration, we're taking the token as the next prediction. So this is what's called auto-regression, right? So we start with to illustrate, let me start with C, and we won't generate anything. We'll just start with C. From C, we're going to generate D. And using just D, we're going to generate E. So what's happening is that the model is actually discarding these tokens and not considering it at all, and only using this last letter as what it's feeding into the input. So here you can see the input to the model is token, and we're using it to predict this value, which is the next token. So we're only looking like at the last token on each iteration.
But then
Yeah.
we get to Z, there's just you get like a random letter because there's nothing that comes after Z. So if you were to just
No, what's the yeah, actually you're right.
if you were to switch C to Z in the generate code.
Yeah, we will get a random letter, you're right. So Z, and then we'll get I, and then we know starting from I, yeah.
Is it like true in all bigram models? You just take the maximum like we have a 1/26 vector, right? So it'll probably be a probability distribution. Or like
Yeah, you can also get a probability distribution. I'm just using argmax for simplicity here, so that you can see like extremely clearly what follows, yeah. One of the things that, as Mateus mentioned, like you can, nothing comes after Z because nothing came after Z in the data set. If we wanted to fix that, we can go to where we define text, and we can put something after Z. What letter would you like after Z? A.
Like these.
Okay, and let's rerun the code. And if everything works, A will be predicted after Z. Okay, run again. And now, do you believe that the next character will be A?
I hope.
There you go.
Okay.
ZAB. And of course, you can play around with the data set. Now, if you actually set it to something like the dog jumped over the fence, a bigram model is far too simple to capture the nuance of the sentence. And so it'll generate something that looks kind of like noise. Oh, the dog jumped over the fence does not contain the letter Z. So we need to put something like D, for example. Oh, and let's make it a little longer. So do you guys see what's happening here? Do you know why this is happening?
Just like looping in the.
Yes.
Because the space, the small follows the space, and then it generates a space and it follows the space again.
Yeah, so what's happening is that after D, it found that the probability, like the token with highest probability of coming after D is the space. And also found that the token with highest probability of happening after the space is T. And then the next highest probability is H, and the next highest probability is E, and the next highest probability is space, and now we just like loop indefinitely. And so even if you put this as like 200, it's just gonna like spit out the like repeatedly. So that's the problem with like only looking at one token at a time. It is true that in this data set, the next most probable token after E is going to be the space and then T, and then it's just going to fall repeatedly. Now, what we're going to see with GPT is that it's going to take in not just the last token, but it's also going to take in a not only the last token, but also it's going to take in like the entire like context window. So when we have like the dog jumped over the fence, it'll first start with, like, I might give it the prompt the, right? So if you give ChatGPT the prompt the, what happens is that it starts with that prompt. It's going to make a prediction for the next token that comes after it. If you're using character level tokenization, then it'll predict space, right? And then what it'll do is it'll take this space and it'll concatenate it with the existing prompt. And then the next most likely character might be D, and then it'll take this D and concatenate it with the existing D prompt. And then it'll predict O, and it'll concatenate O with the existing prompt. Does this make sense? It's generating one character at a time, and every time it generates a character, it'll append it to the existing prompt until it gets to this point. Does that make sense? Yes.
What's the point of doing that?
What's the point at which it stops?
Okay. Like when you sort of, when ChatGPT like takes in like I don't know the first like token that's the, and
Yeah.
adds in like spaces and D, and what does it achieve by doing that?
What is it achieved by doing what?
Like the algorithm or the thing that you just described?
This is how it generates like the response, right? Like the entire response. What I'm trying to say is that the entire response is not really generated all at once, but rather one character at a time. Or in ChatGPT's case, actually one subword at a time.
So like each part of like the sentence generates like a part of the prompt, right? So the will generate a part of it, the dog will also contribute to it. Is that what you're saying?
Or like what I'm saying is that if like let's say I ask it like what is the capital of Japan. What it's gonna do is it's gonna start generating like the next token. ChatGPT uses subword level tokenization, but if it were character level tokenization, it will predict like a space next. This is my prompt. And then like, let's say this is the output. It's first going to take this and it's gonna generate the space. And then it's gonna take this, the next step. So this is step 1. It takes the prompt and generates a space. Step 2 is that it takes that space and concatenates it with the existing prompt. And then it'll predict T. And it'll predict O. And then it'll concatenate with the existing prompt. Does this make sense? This is how it arrives at your answer. Is that clear? Great. And this is also why if you guys use ChatGPT a lot, I'm sure you've noticed that it generates like, not like all at once in one block, but rather like words at a time, right? It'll like do streaming. And the reason is it's generating like tokens, like each token one at a time and appending it back to the prompt. And then continually doing that until it reaches the end. Yes?
So currently with the Pygram model, you're only passing in a single letter in this instance. How would you modify it so that you can pass it like multiple letters?
Yeah. So what's happening here is that we're, if we take a look at the model takes in x, and x is a tensor, and this tensor is going to be used to index the embeddings. Now, what's interesting is that we actually don't have to only pass in one number at a time. If we look at the Pygram model, if we take the model and like take, for example, the tensor, we have to pass in a tensor 0. Torch.tensor. Then we'll get the first row. But we can also like pass it in multiple rows at a time. So for example, 0 and like let's say 25. I actually retrained the data, right? So it might not be the same. But let's just say 0 and 3. And now we have 2 rows of data. So we have the first row and the 4th row of the embeddings table. And so in a real model, such as GPT, you would take the sentence, like, what is the capital of Japan? And then you'll take this thing and convert it into a vector that contains the indexes of the letters. So this might go to like, be converted to, like, let's say 0, 7, 2. And then you'll feed this entire vector into the input of the model. And so in that way, you can feed it a lot more than a single character. You can feed in as many characters as you want up to the context window. So we can't work with this right now because we have only a Pygram model. But what will be really exciting is when we come back and move on to GPT And then we're going to be able to deal with very complicated sentences, actually, in a pretty straightforward manner. So this is actually all for today. I wanted to get across the point of how do we represent language in neural networks? What are embeddings? Why is it useful that we represent embeddings as vectors? And how to, like, some of the machinery that we need to work with text. For example, tokenization, we need to write these like encode and decode functions to generate like these vocab and reverse vocab hash maps, and like some of the infrastructure we need essentially. Next time we'll go through a theoretical explanation of GPT. So part 2 is the theory of GPT. And what I mean by theory is GPT works through some degree of math. And specifically, most of the math it uses is matrix multiplication. So are you all familiar with matrices? Yes. Multiplication. It uses matrix multiplication, and it also uses softmax. It uses a couple of other things too, but if you're familiar like with matrix multiplication, what is a transpose of a matrix? So flip it along the diagonal, and then softmax, then you can understand GPT. And so we're going to be walking through the math of GPT next time, because the math is going to take us from like the numbers that the embeddings represent all the way through to the probabilities of the next output tokens at the end. So we won't be constrained to this like really simple bigram model that only predicts like only looks at one token at a time. We'll look at an entire context window and like go through a lot of mathematical operations to get to the output. So next time, theory of GPT will just be math, but part 3 will be code. The problem with jumping straight into code is that it won't make sense like where it's coming from if you just look at the code, and that's where we have part 2, which is math. So part 2 will be math, and then part 3 will be the code implementation of the math. And if you understand the math, which is not hard at all, by the way, it's basically these 3 operations. If you understand the math, then the code will make a lot of sense. And I think you'll be really amazed at the results we can get by training GPT on our own next time in parts 2 and 3. So that's all for today's lecture. I hope this was useful to you. And